Today, Earth's atmosphere contains 422 parts per million of carbon dioxide. That is the highest level in 3 million years. We know this with precision because we can read the chemical composition of ancient ice and ocean sediments. And we know what happened 3 million years ago at that level of CO2, because that too is written in rock. The temperature was 3 degrees higher. Sea level was 15 to 25 meters higher. The Arctic had no ice in summer. Hippopotamuses lived in Britain. This is not a climate model projection. This is a documented fact. Earth has already lived with our CO2, and it looked nothing like it does today. That world is called the Pliocene, and it is our mirror. Before we continue, please subscribe to this channel. Your support makes this work possible. Thank you. There is a particular kind of scientific evidence that cuts through uncertainty in a way that no model can. It is the evidence of what actually happened. The record of a world that existed, whose chemistry and biology and geography can be reconstructed from the sediments and ice cores and fossils it left behind. Climate projections are necessarily uncertain. They involve assumptions about the future behavior of complex systems, about feedback loops that are difficult to quantify, about the rate at which ice sheets respond to warming. But the Pliocene is not a projection. It is a measurement. 3 million years ago, the atmosphere of Earth contained approximately the same concentration of carbon dioxide it contains today. We know this from multiple independent lines of evidence. From the boron isotope ratios in the shells of foraminifera that record the pH of the ancient ocean, which in turn reflects the concentration of dissolved CO2. From the stomatal density of fossilized leaves, which decreases as atmospheric CO2 rises, because plants need fewer pores to absorb the same amount of carbon. From the carbon isotope ratios in organic marine sediments. All of these proxies, derived from independent chemical systems, converge on the same answer. The mid-Pliocene warm period, from approximately 3.3 to 3 million years ago, had CO2 concentrations in the range of 380 to 450 parts per million. We are currently at 422. We are, in the chemical sense, in the Pliocene. The science of reading the Pliocene climate from rock and sediment is one of the great detective stories of modern geology, and it deserves to be told in some detail because the confidence with which scientists describe a world 3 million years old depends entirely on the quality of the methods used to reconstruct it. Climate scientists do not have a time machine. What they have is a set of chemical and biological recorders, organisms and minerals whose properties are systematically related to the environmental conditions under which they formed, that preserve in their structure a signal of the ancient world that produced them. The most important of these recorders for Pliocene CO2 reconstruction are the foraminifera, single-celled marine organisms with calcium carbonate shells that sink to the ocean floor when they die and accumulate in sediment layers that can be sampled by deep-sea drilling. Foraminifera are sensitive to ocean chemistry in ways that allow paleoclimatologists to extract multiple independent climate signals from a single shell. The ratio of magnesium to calcium in the shell reflects the temperature of the water in which the organism lived. Warmer water produces higher magnesium incorporation. The ratio of oxygen isotopes in the shell reflects both water temperature and the volume of water locked in continental ice sheets. More ice means more of the lighter oxygen isotope is locked in glaciers, leaving the ocean enriched in the heavier isotope. The ratio of boron isotopes in the shell reflects the pH of the ancient seawater, which in turn reflects the concentration of dissolved CO2. More CO2 makes the ocean more acidic, shifting the boron isotope ratio in a direction that can be precisely quantified. These foraminifera-based proxies are complemented by entirely independent lines of evidence from terrestrial archives. The stomatal density of fossilized leaves, the number of pores per unit area of leaf surface through which plants exchange gases with the atmosphere, decreases systematically as atmospheric CO2 rises. Because plants require fewer stomata to absorb the same amount of carbon at higher CO2 concentrations. Fossil leaves from Pliocene deposits in Europe, North America, and Asia. When their stomatal density is measured under microscope and calibrated against modern plants growing under known CO2 concentrations, yield CO2 estimates that are consistent with the boron isotope reconstructions from marine sediments. The agreement between these two completely independent methods, one from ocean chemistry, one from plant physiology, is the foundation of confidence in the Pliocene CO2 record. The alkanone unsaturation ratio, a measure of the degree to which certain lipid molecules produced by coccolithophore algae are chemically unsaturated, provides a third independent temperature proxy from marine sediments, one based on organic geochemistry rather than carbonate chemistry. The TEX-86 paleothermometer, based on the membrane lipids of archaea in ocean sediments, provides a fourth. The fact that all of these proxies, derived from organisms with completely different biochemistries and living in different parts of the water column, produce consistent pictures of Pliocene ocean temperatures, is what gives the Pliomyp temperature reconstruction its authority. The Pliomyp Project, the Pliocene Model Intercomparison Project, coordinates research groups from dozens of institutions across North America, Europe, Asia, and Australia to compile proxy data, run standardized climate model simulations, and compare the results. The most recent phase of the project, Plio-MYP2, established that climate models run with Pliocene boundary conditions and CO2 of approximately 400 parts per million produce global surface temperatures within the range reconstructed from proxy data, and that the spatial pattern of warming, including the polar amplification, the reduced equator to pole temperature gradient, and the warm North Atlantic, is reproduced across multiple independent models. This model data agreement is the scientific basis for using the Pliocene as a constraint on climate sensitivity, the relationship between CO2 and equilibrium global temperature, and for treating the Pliocene world as a reliable guide to the long-term consequences of current CO2 levels. What the proxy data show about the regional expression of Pliocene warmth in Europe is, when examined in detail, a world that was biologically richer, more climatically variable across seasons, and more similar to subtropical Africa than to any modern European landscape. The British Isles, which today support a temperate oceanic climate shaped by the North Atlantic Current, experienced during the Pliocene and the warm interglacial periods of the early Pleistocene conditions roughly equivalent to the modern climate of southern France or northern Spain. The channel between Britain and France, which did not exist as a marine connection during periods of low sea level, but which during the Pliocene high stand was substantially wider than today, was a warm, shallow sea whose sediments have yielded an extraordinary assemblage of marine mollusks, including species now restricted to the Mediterranean or the warm Atlantic coast of Iberia. The Red Crag Formation of Suffolk, a sequence of shelly sands deposited in a warm, shallow sea covering what is now eastern England during the late Pliocene, contains a fauna of marine mollusks that documents the thermal character of the Pliocene North Sea with remarkable precision. Among the species found in the Red Crag are forms now restricted to the Mediterranean, and others whose closest living relatives inhabit the warm coastal waters of West Africa. The temperature implied by this fauna is approximately 3 to 4 degrees above the modern North Sea summer temperatures, a warming that, if applied to the modern North Sea, would make it roughly equivalent to the current summer temperatures of the Bay of Biscay. For the millions of people who live along the North Sea coastline and who rely on its fisheries, this regional comparison is not an abstraction. It is a description of the ocean their coastal cities are moving toward. Moving south through Pliocene Europe, the Italian peninsula and the Iberian peninsula experienced conditions that would today be described as subtropical. Not tropical, but warm enough to support plant communities that are currently restricted to the Canary Islands and the Macaronesian archipelagos, and animal communities that today require the warmth of sub-Saharan Africa. The straight-tusked elephant Paleoloxodon antiquus, a large proboscidean related to but distinct from the modern African and Asian elephants, ranged throughout Europe from the Iberian Peninsula to Poland, and from Britain to Greece during warm periods, feeding on the dense subtropical woodland that covered lowland Europe under Pliocene and interglacial conditions. Adult males reached shoulder heights of approximately 4 meters and body masses estimated at up to 13 tons, substantially larger than the largest modern African elephants, and their ecological impact on the European landscape was correspondingly enormous. A population of animals of that size, browsing and uprooting trees, reshapes the forest structure over decades in ways that promote the woodland grassland mosaic that the pollen record documents. The Merck's rhinoceros and the narrow-nosed rhinoceros were the warm period European rhinos, both substantially different from the woolly rhinoceros that replaced them during cold periods. The European hippopotamus was anatomically very similar to the modern common hippopotamus of Africa, though some studies suggest minor morphological differences that may reflect adaptations to the somewhat seasonal European climate. The spotted hyena, now confined to sub-Saharan Africa, was among the most common and widespread large carnivores of Pliocene and Pleistocene Europe, and its remains are found in cave deposits from Britain to Greece. Machairodonts, the saber-toothed cats, were present in several forms during the Pliocene, including Homotherium, whose remains have been found in North Sea sediments dredged by fishing trawlers, and whose hunting strategy apparently involved ambush attacks on juvenile straight-tusked elephants and other large prey. North Africa in the Pliocene was unrecognizable to anyone whose mental image of the region is formed by the modern Sahara. The Sahara Desert, as a continuous hyper-arid barrier between the Mediterranean and sub-Saharan Africa, is a relatively recent phenomenon. It formed and intensified with the onset of Northern Hemisphere glaciation in the late Pliocene and Pleistocene, as the climate patterns that drive the West African monsoon were reorganized by the growing northern ice sheets and the cooling of the Atlantic. During the Pliocene warm period, before these changes, the Sahara was substantially reduced in extent, or effectively absent across large portions of what is now the most hostile desert on Earth. Pollen records from lake sediments in currently hyper-arid regions of the Sahara document the presence of savanna grasses, acacia woodlands, and freshwater aquatic vegetation during periods when the monsoon penetrated further north than it does today. River systems, whose dry courses are visible in satellite imagery of the modern Sahara, paleo rivers that have been inactive for millions of years, were flowing through a landscape that supported populations of hippopotamus, crocodile, freshwater turtles, and the large herbivore fauna of an African savanna. The green Sahara of the Pliocene has direct implications for North African agriculture and population. The region that is now the world's largest hot desert and that currently supports virtually no rain-fed agriculture was, at the last time CO2 was at current levels, a productive savanna supporting large wildlife populations and, by inference, potentially supportable human agricultural populations orders of magnitude larger than the modern Saharan population. This is the kind of geographic reversal that the Pliocene analogy makes possible, a world in which some of the most densely populated and agriculturally productive modern regions face submergence or thermal stress, while some of the most barren modern regions become productive. The geographic winners and losers of a Pliocene-like future are not distributed randomly. They are written in the geological record of 3 million years ago. The implications of this convergence are profound, and they are not sufficiently appreciated in public discussions of climate change, which tend to focus on what models predict rather than on what the geological record shows. The Pliocene record is not a prediction. It is a constraint. It tells us not what might happen if CO2 reaches current levels, but what did happen when CO2 was at current levels, on a planet with the same sun, the same continents in roughly the same positions, the same ocean basins, the same fundamental physics. The Earth system's response to 400 parts per million of CO2 has already been expressed. It has already been measured. What the Pliocene tells us is not a worst case. It is the equilibrium state. The world that Earth arrives at when it has fully adjusted to a CO2 concentration similar to today's. The question for our century is not whether Earth will move toward that equilibrium. Physics guarantees that it will. The question is how quickly the adjustment occurs. To appreciate why geologists trust the Pliocene analogy as completely as they do, it is worth understanding precisely what the proxy reconstruction process involves, how scientists extract a temperature reading, or a CO2 concentration from a piece of rock or a handful of sediment that has been sitting on the ocean floor for 3 million years. The confidence is not casual. It is the product of decades of methodological refinement, cross-validation between independent techniques, and the accumulated scrutiny of hundreds of research teams working in competition with each other. The workhorse of Pliocene climate reconstruction is the foraminifera, a single-celled marine organism that builds an intricate calcium carbonate shell, lives for a few weeks in the surface or intermediate waters of the ocean, and then sinks to the seafloor when it dies. In the right conditions, below the carbonate compensation depth, where dissolution would destroy them, these shells accumulate in sediment layers at rates of approximately 1 to 10 centimeters per 1,000 years. A 10-meter sediment core from the right ocean floor location therefore contains a continuous record of the organisms that lived in the overlying water column across millions of years, preserved in a sequence of layers that can be dated by their magnetic signature, their microfossil content, and their isotopic stratigraphy. The oxygen isotope ratio of the foraminifera shell, the ratio of the heavier oxygen 18 to the lighter oxygen 16, encodes two signals simultaneously. The first is temperature. Warmer water produces lower oxygen 18 incorporation in the shell, because the fractionation of oxygen isotopes between water and carbonate is temperature dependent. The second is global ice volume. Because the lighter oxygen 16 is preferentially evaporated from the ocean surface and preferentially locked in continental ice sheets during glacial periods, the remaining ocean water becomes enriched in the heavier oxygen 18 when ice sheets are large. By distinguishing these two signals using independent temperature proxies, paleoceanographers can reconstruct both the temperature of the ancient ocean and the volume of ice on land, and therefore the sea level, from a single sediment core. The boron isotope ratio in the foraminifera shell provides the CO2 signal. Boron in seawater exists in two forms, whose relative abundance depends on pH, boric acid, and the borate ion. The shell of a foraminifer incorporates borate preferentially, and the isotopic composition of the boron in the shell therefore records the pH of the ancient seawater. Because the pH of surface seawater is controlled by the equilibrium between dissolved CO2 and carbonate ions, the boron isotope ratio provides a proxy for ancient atmospheric CO2 that is independent of the organic carbon-based proxies. The agreement between boron isotope CO2, reconstructions from marine sediments and stomatal density, CO2 reconstructions from fossil leaves, two proxies based on completely different chemical systems in completely different archives, is the strongest evidence for the reliability of the Pliocene CO2 record. The magnesium to calcium ratio in the foraminifera shell provides an independent temperature proxy based on the temperature-dependent incorporation of magnesium into the calcium carbonate lattice. The alkanone unsaturation index, based on the degree of chemical unsaturation in lipid molecules produced by coccolithophore algae, provides a fourth independent temperature proxy from organic molecules preserved in the same sediment. The TEX86 thermometer, based on the membrane lipids of archaea, provides a fifth. The fact that all 5 of these independent proxies, based on organisms with completely different biochemistries operating in different parts of the water column, produce consistent pictures of Pliocene ocean temperatures, gives the Pliomyp reconstruction an authority that no single proxy could achieve alone. The Pliomyp project, the Pliocene Model Intercomparison Project, is the international scientific framework that coordinates this reconstruction effort. Dozens of research groups across North America, Europe, Asia, and Australia contribute proxy data from sites distributed across every ocean basin and every continent. And these data are assembled into a coherent global reconstruction of Pliocene surface temperatures, precipitation patterns, and ice sheet extent. Climate models are then run with Pliocene boundary conditions, the known continental configuration, the reduced ice sheets, the elevated CO2, and their output is compared against the proxy reconstruction. In Pliomyp2, the most recent phase, the climate models and the proxy data show agreement that is remarkable by any standard of paleoclimate science. The spatial pattern of warming, the magnitude of polar amplification, the reduced equator to pole temperature gradient, and the warm North Atlantic are all reproduced across multiple independent models, running with approximately 400 parts per million of CO2. This model data agreement is the scientific foundation for using the Pliocene as a constraint on climate sensitivity, the fundamental parameter that determines how much warming results from a given increase in CO2. The thermal commitment, the concept that the climate system has not yet fully responded to the CO2 that is already in the atmosphere, deserves its own careful explanation because it is arguably the most important and least intuitively understood aspect of the Pliocene analogy. The atmosphere warms relatively quickly in response to rising CO2 within years to decades because it has low thermal mass. The ocean warms far more slowly because it has an enormous thermal mass. And because the deep ocean, which constitutes 90% of the ocean's volume, exchanges heat with the surface only over centuries. The ice sheets are slower still. They respond to sustained warming over centuries to millennia, as the balance between accumulation and melting gradually shifts. The result is that at any given moment, the observed warming is only a fraction of the warming that current CO2 levels will eventually produce. At current CO2 levels of approximately 422 parts per million, the immediate observed warming is approximately 1.3 degrees above pre-industrial. But the equilibrium warming, the warming that will eventually be realized as the ocean fully absorbs the heat being trapped by the elevated CO2, and as the ice sheets reach the volume appropriate for the new temperature regime, is estimated by the Pliomyp data and by independent climate sensitivity studies at approximately 2.5 to 3.5 degrees above pre-industrial. The Pliocene, at roughly the same CO2, was approximately 2 to 3 degrees warmer than pre-industrial globally. The agreement between these numbers is not coincidental. It is the system telling us, from two independent directions, what the equilibrium state looks like. We are currently about 1.5 to 2 degrees below the equilibrium temperature for our CO2 concentration. The heat is already in the atmosphere. The ocean is absorbing it. The ice is beginning to melt. The system is moving toward the Pliocene, and it will continue to move toward it, regardless of what emissions decisions are made in the coming decades, because the CO2 that drives the commitment is already present. The thermal commitment at current CO2 levels is not the end of the story. It is the floor. The closing of the Panama Seaway, the tectonic event that completed the Isthmus of Panama approximately 3.5 to 3 million years ago, and that fundamentally reorganized global ocean circulation, is worth understanding as context for the Pliocene climate, because it illustrates how the geological setting of the Pliocene was not identical to today, even though the CO2 was similar. Before the isthmus closed, warm tropical water circulated freely between the Atlantic and Pacific Oceans across the shallow Central American Seaway, distributing equatorial heat more broadly and reducing the temperature gradient between tropical and polar regions. When the seaway closed, this circulation was blocked, and the warm, salty surface water of the equatorial Atlantic was redirected northward into the nascent Gulf Stream system, transporting heat and moisture to the high latitudes of the North Atlantic and Arctic. This reorganization contributed to the eventual onset of Northern Hemisphere glaciation approximately 2.7 million years ago. But during the warm Pliocene, before the ice sheets had grown large, the new Gulf Stream-dominated Atlantic circulation produced a North Atlantic that was several degrees warmer than today. The lesson for climate sensitivity calculations from the Pliocene is that some of the Pliocene warmth was attributable to this different ocean circulation pattern, rather than to CO2 alone. A complication that the PLIOMIP project explicitly accounts for by treating the different continental configuration as a boundary condition in the model runs, and by careful comparison of model output against the spatial pattern of the proxy data. The Pliocene epoch spans from approximately 5.3 to 2.6 million years ago, the last epoch of the Cenozoic era before the Pleistocene, the age of ice ages that immediately preceded our own geological moment. In geological terms, it is extraordinarily recent. The continents were essentially in their modern positions. The Atlantic Ocean, the Pacific Ocean, the Indian Ocean were where they are today. The Mediterranean Sea existed. The Alps and the Himalayas were near their modern heights. Africa was cooling and drying, and its savannas were forming in a pattern that would drive the evolutionary radiation of the hominins, the lineage that leads to us. The Pliocene is not an alien world. It is our world with a different thermostat setting. The most important event in the Pliocene for understanding Earth's climatic history was the closing of the Central American Seaway, the shallow ocean connection between the Atlantic and Pacific Oceans that was progressively restricted by the volcanic and tectonic activity that built the Isthmus of Panama, completing its closure approximately 3.5 to 3 million years ago. Before the isthmus closed, warm tropical water could flow freely between the Atlantic and Pacific. distributing heat from the tropics across a much wider equatorial ocean and reducing the temperature gradient between equatorial and polar regions. When the isthmus closed, this tropical heat exchange was blocked. The warm, salty surface water of the equatorial Atlantic was redirected northward into what is now the Gulf Stream, transporting heat toward the high latitudes of the North Atlantic and delivering more moisture to the atmosphere above Greenland and the Canadian Arctic. This increased moisture delivery, combined with the slight cooling trend of the late Pliocene as CO2 began to decline, eventually triggered the onset of Northern Hemisphere glaciation approximately 2.7 million years ago. The glaciations that would define the Pleistocene and that produced the ice ages of the past 2 million years. But before that cooling, during the mid-Pliocene warm period from 3.3 to 3 million years ago, the Earth was warm, substantially warmer than today, despite having approximately the same CO2. This apparent paradox deserves explanation. If the CO2 was the same, why was the temperature higher? The answer lies in a concept called the commitment temperature, or equilibrium climate sensitivity, the amount of warming that ultimately results from a given CO2 concentration. Once all the slow feedbacks have had time to operate, the ocean takes centuries to fully absorb heat. Ice sheets take centuries to millennia to grow or shrink. Vegetation patterns shift over decades to centuries. When CO2 rises, the immediate atmospheric warming is only a fraction of the eventual warming. The rest is stored in the thermal inertia of the ocean and will be realized over subsequent centuries and millennia as the system reaches equilibrium. The mid-Pliocene warm period represents a world that had time to reach approximate equilibrium with its CO2 concentration. We have been at or above 400 parts per million for only a few years. Our current temperature, roughly 1.3 degrees above pre-industrial, is the initial response, not the equilibrium response. The Pliocene temperature tells us what the equilibrium looks like. The reconstruction of Pliocene temperature is one of the most intensively studied problems in paleoclimatology, and the data assembled by the Pliocene Research, Interpretation and Synoptic Mappings Project, Plio-MIP, represents decades of proxy data collection and climate model validation from sites around the world. The picture that emerges is distinctive and, for a person living in the 21st century, deeply personal. Global mean surface temperature during the mid-Pliocene warm period was approximately 2 to 3 degrees Celsius higher than the pre-industrial baseline. This sounds modest. A few degrees is the range between a cool summer day and a warm one. But global mean temperature is the average of enormous geographic variability, and the warming was not distributed evenly. It was concentrated at high latitudes in a pattern that paleoclimatologists call polar amplification. The same pattern that modern observations show is already underway today. Research published in AGU Advances in January 2025 by Tierney and colleagues at the University of Arizona, using a technique called paleoclimate data assimilation that combines proxy records with climate model physics to produce spatially complete reconstructions of past climate states. found that the mid-Pliocene warm period warming was 2 to 3.5 degrees globally, but reached 8 to 14 degrees above modern values in the Arctic during summer. The Arctic summer warmth of the Pliocene was not merely a consequence of sea ice loss. It was also driven by a substantial poleward shift of the tree line, with boreal forests replacing tundra across much of what is now the Arctic tundra zone of Canada, Siberia, and Alaska. Trees are dark. They absorb more solar radiation than the pale tundra vegetation they replaced. This surface albedo feedback, the conversion of a reflective surface to an absorbing one, amplified the warming driven by CO2 alone, pushing Arctic summer temperatures to levels that seem extraordinary from the perspective of the world we know today. A study published in PNAS in February 2026 by Sorensen, Polisar, and colleagues at the University of Colorado Boulder examined the temperature record from the northern tropical Andes, a region that had been largely absent from Pliocene climate reconstructions, by analyzing biomarkers preserved in lake sediments, from sites at 4 degrees north latitude in Colombia at an elevation of approximately 3,000 meters. The study found that land temperatures in the tropical Andes during the Pliocene were approximately 1 to 2 degrees higher than the simultaneously recorded ocean surface temperatures from the same region. This tropical land amplification, the tendency for continental surfaces to warm more than the adjacent ocean under elevated CO2, has important implications because 40% of the world's population lives in the tropics. If the Pliocene analogy holds, the tropical land warming that awaits us at current CO2 levels is not simply the global average of 2 to 3 degrees, but a larger number, closer to 3 to 5 degrees, in the continental interiors of Africa, South America, and Southeast Asia, where most of the world's tropical population lives. The sea level of the Pliocene is, for most people, the single most viscerally comprehensible piece of Pliocene climate information. When geologists say the sea level was 15 to 25 meters higher than today, they are saying something that can be translated directly into a map of the modern world. London, underwater to approximately the height of a 5-story building, with the Thames estuary expanded to cover what is now the city centre. New York, the Manhattan skyline rises above the Pliocene Sea, but much of Long Island and New Jersey is submerged. Miami, completely submerged, as is essentially the entirety of South Florida. New Orleans, underwater. Bangladesh, largely underwater. The Netherlands, largely underwater. The North China Plain, where more than 100 million people live at elevations below 20 meters, substantially inundated. The total global population currently living below 25 meters of elevation is in the billions. The Pliocene sea level tells us not what might happen if warming continues, but what has already happened at the CO2 concentration we have already reached. The source of the Pliocene sea level high stand is ice that no longer exists. At current sea levels, the world's ice is distributed primarily among 3 systems. The East Antarctic ice sheet, which contains approximately 58 meters of sea level equivalent if fully melted. The West Antarctic ice sheet, which contains approximately 3.5 meters. And the Greenland ice sheet, which contains approximately 7 meters. Full melting of all 3 is not the Pliocene scenario. The East Antarctic ice sheet was largely intact during the Pliocene, though some of its marine basins may have retreated substantially. The Pliocene sea level high stand is attributed primarily to the partial or near complete loss of the West Antarctic ice sheet, the partial loss of the Greenland ice sheet, and the loss of various smaller ice bodies in the Northern Hemisphere that no longer exist in any form today. Research published in Nature Communications in July 2025 by Comas Brew and colleagues at the University of Reading and the British Antarctic Survey provides new geochemical evidence for the transition of the West Antarctic ice sheet from its smaller Pliocene configuration to its more expanded modern state. The study, based on analysis of sediment cores from the Amundsen Sea, the region adjacent to the currently most rapidly melting sectors of the West Antarctic ice sheet, including the Thwaites and Pine Island glaciers, found that the West Antarctic ice sheet grew substantially in the late Pliocene and early Pleistocene as temperatures fell and CO2 declined. The implication, running in reverse, is that as CO2 rises and temperatures increase towards Pliocene levels, the trajectory for the West Antarctic ice sheet is toward its smaller Pliocene configuration, a configuration associated with 3 to 5 meters of additional sea level rise from West Antarctica alone, on top of contributions from Greenland and other ice bodies. The timescale on which this sea level rise occurs is the most debated question in modern glaciology. The Pliocene tells us the destination. It does not straightforwardly tell us the rate of travel. Ice sheets are not passive responders to temperature. They have complex internal dynamics, including marine ice cliff instability and marine ice sheet instability that can cause rapid non-linear retreat once certain thresholds are crossed. Research published in Earth System Dynamics in October 2025 by Bader and colleagues using the EC-Earth-3 climate model forced with the PRISM 4D Pliocene ice sheet reconstruction, found that the Pliocene polar southern hemisphere responded substantially to the reduced West Antarctic ice sheet configuration, with ocean circulation changes, sea ice patterns, and precipitation patterns differing significantly from their modern counterparts. The modeling suggests that once the West Antarctic ice sheet retreats to its Pliocene extent, the resulting changes in ocean circulation and sea ice create feedback conditions that tend to maintain the reduced ice extent, a self-reinforcing system that makes recovery to modern ice volumes unlikely without a substantial reduction in CO2 below current levels. To understand what that sea level and temperature increase actually looked like on the ground, in the landscape, in the ecosystems, in the distribution of animals and plants, the best evidence comes not from computer models, but from the Pliocene fossil record of Europe, which is among the most densely sampled paleontological records in the world. What the European fossil record of the Pliocene shows is, to a modern observer, genuinely startling. The British Isles during the Pliocene were warmer, wetter, and more biologically diverse than they are today by a substantial margin. The mean annual temperature of what is now southern England was approximately 3 to 4 degrees higher than the modern value, roughly equivalent to the current climate of the Loire Valley in France or of the Iberian Peninsula. The flora of Pliocene. Britain included plant taxa that are now restricted to southern Europe or the Mediterranean basin. Evergreen oaks, laurels, and members of the walnut family grew alongside still present species like elm, lime, and alder. The forests of Pliocene Britain were denser, taller, and structurally more complex than the modern managed and fragmented woodlands they have replaced. More similar in character to the subtropical forests of the Azores or the Canary Islands than to the oak and ash woodlands that now represent the characteristic British natural vegetation. But the most viscerally memorable evidence for Pliocene Britain's character comes from the mammal bones. Excavations in the Norwich Crag Formation of East Anglia, in the Cromer Forest bed, and, most memorably, beneath Trafalgar Square in central London, have produced an extraordinary fauna of warm climate mammals that inhabited the British Isles during the warm interglacial periods of the late Pliocene and early Pleistocene, when temperatures approached or exceeded Pliocene levels. Hippopotamus remains, teeth, bones, sometimes complete skulls, have been found at numerous sites across southern England. The Trafalgar Square, hippopotamus, excavated during construction works in the 19th and 20th centuries, is one of the most famous of these finds. The bones of a large hippopotamus that lived in what was then a broad, slow-moving, warm river, flowing through a landscape that more closely resembled the modern Nile Valley or the Zambezi floodplain than anything recognizable as the Thames. Straight-tusked elephants, considerably larger than modern African elephants, ranged as far north as what is now Germany and Poland. Lions, narrow-nosed rhinoceroses, spotted hyenas, and several species of large deer completed a megafauna that would be immediately recognizable to any visitor to the modern African savanna, but that has no modern European counterpart. Research published in a 2026 paper in the journal Vertebrate Paleontology by Sorrentino and colleagues, examining a hippopotamus mandible from lacustrine deposits near Ortona in the Abruzzo region of Italy, contributes to our growing understanding of the ecological diversity of European hippopotamus populations during the Pliocene and Pleistocene. The paper is part of a substantial body of recent work examining the phenotypic diversity of what were, during the warm periods of the late Pliocene and early Pleistocene, common and widely distributed elements of the European megafauna. The hippopotamus of Pliocene and Pleistocene Europe was not a rare vagrant pushed to the extreme of its range. It was a characteristic component of the warm period European ecosystem, present wherever there were rivers large enough to accommodate its semi-aquatic lifestyle, which, under Pliocene climatic conditions, meant most of the major river systems of Western and Central Europe. The ecological reconstruction of Pliocene Europe, published in Biological Conservation in February 2026 by Svenning Czyżewski and colleagues at Aarhus University and the University of Warsaw, represents one of the most comprehensive recent syntheses of Pliocene and Pleistocene European paleoecology. The paper examines pollen records, macrofossil data, and ecological indicator values for plant species to reconstruct the structure and composition of European vegetation during warm periods when CO2 was near current levels. The findings challenge the conventional reconstruction of Pliocene Europe as a region of closed canopy forest. The pollen data, corrected for the known biases in pollen representation, consistently suggest that Pliocene European vegetation was more open than modern temperate forest. A woodland grassland mosaic in which large herbivores played a critical role in maintaining openness through browsing and grazing. The giant deer, the straight-tusked elephant, the woolly rhinoceros's warm period ancestors, the hippopotamus, all were the engineers of a dynamic landscape that oscillated between woodland and grassland, depending on herbivore pressure and climate variation. Moving south and west from Britain, the Pliocene Mediterranean world was, in many respects, the most dramatically different from its modern counterpart. The Mediterranean basin of the Pliocene was warmer and more humid than today. The Sahara Desert, which formed largely during the intensification of Northern Hemisphere glaciation in the late Pliocene and Pleistocene, was either absent or much reduced in extent, replaced by savanna and woodland. The Atlas Mountains of Morocco and Algeria supported forests of subtropical character. The Nile Valley was more productive and its delta more extensive. The Arabian Peninsula, now one of the most arid regions on Earth, may have supported grassland and scrub vegetation across much of its interior. The concept of the Pliocene as a time when the Sahara was green, a concept supported by pollen records, river systems now buried beneath desert sands, and the distribution of fossil vertebrate fauna, fundamentally alters the picture of what North Africa and the broader Mediterranean world looked like at the last time atmospheric CO2 was comparable to today. The tropical regions of the world are where the Pliocene climate data become most alarming in their implications. And the PNAS February 2026 paper by Sorensen and Polisar is the most directly relevant recent study. By establishing a high-resolution temperature record from the tropical Andes covering approximately 4 million years, the study documents not only the absolute temperatures of the Pliocene warm period in the tropics, but the pattern of tropical land amplification, the tendency for continental land surfaces in the tropics to warm more than the adjacent ocean. The finding that tropical land temperatures during the Pliocene exceeded simultaneous ocean temperatures by 1 to 2 degrees is consistent with what modern climate models predict for tropical land amplification under elevated CO2. And it has direct consequences for the hundreds of millions of people who live in tropical continental interiors. The primary concern for the tropics under Pliocene-like conditions is not inundation. Most of the world's tropical population lives at elevations well above sea level, but heat and water, the wet bulb temperature threshold, the combination of temperature and humidity above which the human body can no longer cool itself through sweating and which causes death within hours of sustained exposure, is approximately 35 degrees wet bulb, or approximately 55 degrees Celsius at low humidity. Pliocene tropical land temperatures of 3 to 5 degrees above the pre-industrial baseline would push wet bulb temperatures in the most humid tropical regions: the Congo Basin, the Amazon, the Indo-Gangetic Plain of South Asia, the river deltas of Southeast Asia, significantly closer to this lethal threshold. Modern climate science suggests that periods of wet bulb temperatures above 32 degrees already occur occasionally in these regions. At Pliocene tropical temperatures, such conditions would become substantially more frequent and more geographically extensive. The monsoon systems that deliver most of the precipitation to the world's tropical and subtropical agricultural zones were also substantially different in the Pliocene. The intensification of the East Asian summer monsoon, the Indian summer monsoon, and the West African monsoon during warm periods is well documented in the proxy record. More energy in the climate system means more vigorous atmospheric circulation and more intense precipitation during the monsoon season. But more intense monsoon rainfall does not straightforwardly translate into better agricultural conditions. It means more extreme wet seasons, more intense flooding, more soil erosion, and potentially longer dry seasons, as the seasonal precipitation becomes more concentrated into shorter, more intense episodes. The agricultural systems of South Asia and Sub-Saharan Africa, which feed more than 2 billion people, evolved under the climate variability of the Holocene, not the Pliocene. The shift to Pliocene conditions represents not merely a warmer world, but a world with fundamentally different precipitation patterns, for which the current agricultural infrastructure was not designed. The ocean circulation of the Pliocene was distinct from the modern in ways that had significant regional climate consequences. The Atlantic, meridional overturning circulation. The system of deep water formation and northward surface flow that includes the Gulf Stream, and that is responsible for the anomalous warmth of northwestern Europe relative to other regions at the same latitude, appears to have operated differently in the Pliocene, with some evidence from deep-sea sediment records suggesting a shallower and more variable overturning than today. The closure of the Panama Seaway, which was only recently completed as the Pliocene began, was still reorganizing the pattern of heat transport between the Atlantic and Pacific, and the distribution of warm water in the North Atlantic was substantially different from the modern pattern. The North Atlantic was warmer, sea surface temperature. Reconstructions show anomalies of 3 to 5 degrees above modern values across much of the basin. And the seasonal sea ice that now forms in the northern Labrador Sea and Greenland Sea was largely or entirely absent. The Arctic Ocean in the Pliocene is among the most striking paleoclimate results, and it is documented with unusual directness by the lake sediment core from Lake El-Gigitgin in northeastern Siberia, the result of a meteorite impact 3.6 million years ago that created a basin whose undisturbed sediment record spans the entire Pliocene. The El-Gigitgin core, analyzed by Mellers, Brigham Greta, and colleagues at the University of Cologne and the University of Massachusetts, found that Arctic summer temperatures during the mid-Pliocene warm period were approximately 14 degrees above modern values, a number that is not a model prediction, but a measurement from a physical sediment core. At those temperatures, the Arctic was not merely ice-free in summer. It was warm. The lakes of Arctic Siberia that today thaw for 2 months a year were open water for 5 or 6 months. The tundra was replaced by boreal forest. The permafrost that currently underlies approximately a quarter of the Northern Hemisphere's land surface, and that stores enormous quantities of carbon in frozen organic matter, was substantially reduced in extent. The permafrost of the modern Arctic is itself a significant climate feedback in the transition toward Pliocene conditions. As temperatures rise and permafrost thaws, the frozen organic matter, accumulated over thousands of years under conditions where decomposition was too slow to process all the biological material being deposited, begins to decompose. Decomposition releases CO2 and methane. The release of these greenhouse gases from thawing permafrost constitutes a feedback loop. Warming thaws permafrost. Permafrost releases carbon. Released carbon drives further warming. Further warming thaws more permafrost. This feedback was not present as a driver of the Pliocene warm period. The Pliocene preceded the accumulation of the vast permafrost carbon reservoir that now exists, but it is present as a potential accelerant of the warming that is currently moving Earth toward Pliocene conditions. The International Permafrost Association estimated in its 2025 assessment that the Northern Hemisphere permafrost zone currently stores approximately 1,500 gigatons of carbon, roughly twice the amount currently in the atmosphere, of which a significant fraction is in the upper layers most vulnerable to near-term thaw. The coral reefs of the Pliocene world were distributed differently from those of today, reflecting the different sea surface temperature patterns. Coral reef ecosystems in the modern world are concentrated in the tropical Pacific, Indian Ocean, and Caribbean, with their upper thermal limit being approximately 29 degrees Celsius. In the Pliocene, the warm pool of the equatorial Pacific, the region of warmest surface temperatures that drives global atmospheric circulation, was larger and extended further east than today, creating reef-friendly conditions in areas that are now too cold or too variable for coral. At the same time, the warming of the upper thermal limit, as temperatures rose above the coral bleaching threshold, would have stressed the same reef systems that currently support the highest marine biodiversity on Earth. The Pliocene coral record is complex and not fully resolved, but the broad picture is one of geographic redistribution of reef ecosystems, with some regions gaining and others losing reef-building conditions, and with the net effect on global coral diversity remaining a subject of active research. The question that haunts every serious engagement with the Pliocene analogy is the question of time. The Pliocene warm period did not begin when a geological instant of CO2 increase occurred. It developed over hundreds of thousands of years as slow geological and astronomical processes gradually raised CO2 and maintained it at elevated levels. The ice sheets that melted during the Pliocene melted over similar timescales, not in decades or centuries, but in millennia, as the slow response of ice dynamics to sustained warmth gradually eroded the ice volume. This raises a question that is simultaneously hopeful and sobering. If we are at Pliocene CO2 now, how long does it take to get to Pliocene sea levels? The honest answer, supported by the best current science, is we do not know precisely. But the range of uncertainty does not span centuries at the low end. It spans centuries to a few millennia. The thermal commitment of current CO2 levels, the warming that will be realized even if emissions were halted today, is estimated at approximately 1 to 1.5 additional degrees above current temperatures, taking the long-term equilibrium to approximately 2.5 to 3 degrees above pre-industrial levels, well within the Pliocene range. The sea level commitment is larger and takes longer to realize because ice sheets are slow. But the direction is fixed. The physics of a 3-degree world with current CO2 includes 15 to 25 meters of sea level rise. The only variable is the century on which this becomes the coastline rather than the geology. What makes the Pliocene analogy uniquely valuable and uniquely uncomfortable is precisely that it removes the qualification of uncertainty that surrounds every climate projection. Climate projections can be disputed. Computer models can be criticized. Scenarios can be debated. But the Pliocene cannot be disputed in the same way. It happened. Its temperature is recorded in the chemistry of foraminifera shells. Its sea level is recorded in the elevation of ancient beach terraces on every continent. Its vegetation is recorded in the pollen preserved in lake sediments. Its animal life is recorded in the bones found under Trafalgar Square. You are not arguing with a model when you look at the Pliocene. You are looking at the record of what the Earth system does when it equilibrates to approximately 400 parts per million of CO2. The Pliocene does not tell us that civilization will collapse or that humanity will perish. The Pliocene was a habitable world. Animals lived in it. Plants grew in it. Some of the most successful mammalian lineages of the Cenozoic thrived in it. What it tells us is that the habitable geography shifts, that the coastlines move, that the deserts and forests swap places, that the productive agricultural zones reorganize, that the megacities of the modern world that were built at elevations and latitudes appropriate for the Holocene are not appropriate for the Pliocene. It tells us that the transition from the Holocene to a Pliocene-like state involves not the end of life on Earth, but the largest forced migration and geographical reorganization in the history of human civilization. The permafrost beneath the Siberian and Canadian plains that locks away twice the atmosphere's carbon is already beginning to thaw. We have already, chemically, arrived in the Pliocene. The sea level figure has been established. What it means for specific cities requires a direct calculation. Shanghai, with a population of approximately 24 million people and a metropolitan area that is the economic engine of the world's second largest economy, sits at an average elevation of approximately 4 meters above current sea level. The entire Yangtze River Delta urban complex, which includes not only Shanghai, but Suzhou, Wuxi, Hangzhou, and dozens of other cities with combined populations exceeding 60 million, lies largely below 10 meters of elevation. At Pliocene sea levels, this region would be under 10 to 20 meters of water. The farmland of the Yangtze Delta, which for millennia has been among the most productive agricultural land in the world, would not exist. The infrastructure, The ports, the factories, the transportation networks, the power generation facilities. That makes the Yangtze Delta, the manufacturing center of the global economy, would not exist. Mumbai, with a population of approximately 21 million people, on a peninsula that projects into the Arabian Sea at an average elevation of approximately 10 to 15 meters, would be substantially or entirely submerged at Pliocene sea levels, depending on which estimates of sea level high stand are used. The 7 islands that were joined by reclamation projects to form modern Mumbai sit at elevations ranging from a few meters to approximately 60 meters at the highest points of Malabar Hill. At 15 meters of sea level rise, the historic center, the port, the industrial areas, and the low-lying residential districts that house the majority of Mumbai's population would be underwater. The financial district, the port, the railway termini, all of these would be submerged. Jakarta, the capital of Indonesia and one of the most rapidly sinking cities on Earth due to groundwater extraction, has an average elevation of approximately 8 meters above current sea level, with large portions of the city already below sea level and held above water only by drainage infrastructure. At Pliocene sea levels, Jakarta and the entire northern coastal plain of Java would be underwater. The Indonesian government has already recognized this trajectory and is in the process of relocating the national capital to the higher elevation interior of Borneo, a decision driven by current sea level trends that represents, in effect, a preparation for conditions that the Pliocene record shows are the geological destination. New Orleans, built largely on river delta sediments at or below current sea level and protected by an extensive levee system, would face inundation of catastrophic proportions. The entire city and its surrounding region under 10 to 20 meters of water. Miami and South Florida, built on limestone karst, at elevations averaging approximately 2 meters above sea level, would be completely submerged. The Florida Peninsula, south of approximately Orlando, would effectively cease to exist as land. The Gulf Coast of Texas and Louisiana, the heart of the American oil and gas industry, and one of the most important petrochemical manufacturing regions on Earth, would be broadly inundated. London, protected today by the Thames Barrier against current storm surge levels, sits at an average elevation of approximately 11 meters above sea level in its historic center, with the River Thames currently flowing at sea level through the heart of the city. At 15 meters of sea level rise, the Thames would become a wide tidal estuary extending well into what is now central London. The City of London, the historic centre and financial district, would be at or near the inundation threshold. The low-lying areas of East London, including much of Docklands and the Thames estuary communities of Essex and Kent, would be underwater. The bones of hippopotamuses found beneath Trafalgar Square would be found, if the Pliocene sea level were to be restored, at the bottom of a shallow marine bay. Precisely the environment they imply existed there 3 million years ago. The agricultural consequences of Pliocene-like conditions extend beyond the submergence of delta and coastal farmland. The grain-growing regions of the world, the American Midwest, the North China Plain, the Indo-Gangetic Plain, the Ukrainian and Russian steppe, the Brazilian Cerrado, were shaped by the Holocene climate patterns of the past 10,000 years. Specific distributions of rainfall, frost dates, growing seasons, and soil moisture that support the varieties and agricultural practices on which global food security depends. Under Pliocene conditions, several of these regions face pressures that are not primarily about sea level, but about temperature, precipitation, and their interaction with soil biology. The American Midwest, which produces approximately 30% of the world's corn and soybean exports, sits at elevations well above any projected sea level rise, but faces a different Pliocene pressure. The combination of higher temperatures and altered precipitation patterns that in the Pliocene produced conditions closer to those of the modern Great Plains and mixed grass prairie, rather than the productive corn belt. Paleoclimate data for the central North American region during the Pliocene suggest that summer temperatures were 2 to 4 degrees higher than today, and that summer precipitation was more variable, with longer dry spells between rain events, conditions that are physiologically stressful for the high-yielding corn and soybean varieties on which modern American agriculture depends, and that would require substantial adaptation in crop varieties, irrigation infrastructure, and farming practices. The Indo-Gangetic Plain of South Asia, the agricultural heartland of India and Pakistan, feeding approximately 1.6 billion people, faces a combination of Pliocene pressures that is arguably the most severe of any major agricultural region. Rising temperatures push wet bulb values closer to physiological limits during summer heat waves. The Himalayan glaciers that currently provide dry season irrigation water to hundreds of millions of farmers are projected to lose substantial mass under Pliocene-like conditions, reducing the reliable summer water supply precisely when temperature-driven evaporation and crop water demand are highest. And the intensity of the Indian summer monsoon, the source of 80% of India's annual precipitation, is projected to increase under elevated CO2, producing more extreme rainfall events and more intense flooding that damages crops, erodes soils, and overwhelms drainage infrastructure, even as the periods between monsoon events become longer and drier. What does it mean to know all of this, to have read everything the Pliocene record contains? This is the question that sits at the end of every serious engagement with the Pliocene analogy, and it is not a scientific question. It is a question about how humans process information about their situation, when the information is simultaneously certain and almost unbearably consequential. The scientific consensus on the committed timeline is, in its essentials, clear. The thermal commitment at current CO2 levels, the warming that will occur even if emissions stopped today, is approximately 1 to 1.5 additional degrees, which would bring equilibrium temperatures to approximately 2.5 to 3 degrees above pre-industrial, well within the Pliocene range. The sea level commitment is larger and slower. The best current estimates suggest that the committed sea level rise from current CO2 levels, realized over centuries to millennia, is in the range of 6 to 10 meters, well above current sea levels, but below the full Pliocene high stand of 15 to 25 meters, reflecting the fact that current CO2 is at the lower end of the Pliocene range and that full equilibration takes geological time. But if CO2 continues to rise, as it has every year since systematic measurements began, The committed sea level rises accordingly, and the timescales compress as ice dynamics respond to sustained warmth. The International Panel on Climate Change's most recent assessment, and the research it synthesizes, identifies the West Antarctic ice sheet as the most immediate source of potential rapid sea level rise, with marine ice sheet instability mechanisms capable of producing meters of sea level rise within centuries rather than millennia under sustained warming above 1.5 to 2 degrees. The Nature Communications July 2025 study on West Antarctic ice sheet history confirms that the ice sheet was substantially smaller during the Pliocene, a direct geological validation of the models suggesting it can reach that smaller state again, and of the ice dynamics research suggesting that marine ice sheet instability may accelerate that transition once warming crosses a threshold that current trajectories suggest will be reached within decades. That threshold has already been crossed. The remaining question is not whether, but how fast. The question of whether the sea level eventually rises 15 meters or 25 meters depends on how much further CO2 rises from the current level. The question of whether the agricultural reorganization occurs over 3 centuries or 10 centuries depends on the rate at which the ice responds. These are important questions for planning purposes. They do not change the destination. They change only how quickly one arrives there and how much time is available to adapt. The countries and regions that stand to gain from a Pliocene-like climate reorganization are as real as those that stand to lose, and their identification is one of the more counterintuitive aspects of the Pliocene analogy. The same warming that submerges coastal megacities and desiccates tropical agricultural zones opens new productive landscapes at high latitudes that are currently constrained by cold and by permanently frozen soil. Siberia, currently the world's largest region of continuous permafrost, supporting sparse larch forests and tundra over an area larger than Canada, was, during the Pliocene, a landscape of boreal forest extending to latitudes well north of the modern treeline, with summer temperatures comparable to those of the modern Canadian prairies. As permafrost thaws and the treeline moves northward, the soils of Siberia, which contain extraordinary quantities of organic material accumulated over millennia of slow decomposition, become available for agricultural use for the first time. Russian agricultural scientists have estimated that the warming of Siberia under elevated CO2 scenarios could open hundreds of millions of hectares of new agricultural land over the course of the century. The qualification is significant. The soils that emerge from permafrost thaw are initially waterlogged, nutrient-poor, and structurally unstable, requiring decades of drainage and management before they become agriculturally productive. The transition from frozen tundra to productive farmland is not instantaneous. It is a multi-generational agricultural investment. But the trajectory, under Pliocene-like conditions, runs clearly in the direction of a more agriculturally productive Siberia and northern Canada. Greenland, currently covered by an ice sheet averaging approximately 2 kilometers in depth and supporting no permanent agricultural population, had, during the Pliocene and the warm interglacials of the Pleistocene, ice-free coastal margins with soils capable of supporting boreal forest and tundra vegetation. Pollen records from Pliocene sediments beneath the modern Greenland ice sheet document the presence of spruce forests at what is now ice-covered terrain. As the Greenland ice sheet recedes under Pliocene-like conditions, a process that will take centuries to millennia to reach Pliocene extent, but whose direction is determined by the committed warming, the coastal fjords and lowlands of Greenland become available for the first time in millions of years. The Norse settlements of medieval Greenland, which maintained sheep farms and cattle ranches on the ice-free coastal margins for approximately 5 centuries before the climate cooled in the Little Ice Age, provide a historical demonstration of Greenland's agricultural potential under conditions somewhat warmer than today. The Mediterranean basin presents the most complex picture among the regions facing Pliocene-like climate reorganization. Complex because the Pliocene Mediterranean was, in some dimensions, more productive than today, and in others more extreme. The reduction of the Sahara during warm periods, which brought more moisture and vegetation to North Africa, and potentially transformed some of the world's most hostile desert into productive savanna, represents a potential gain for a region currently facing severe water stress. But the Mediterranean climate, characterized by dry summers and wet winters, is projected to become substantially drier under elevated CO2 as the subtropical dry zones expand poleward, pushing the Mediterranean precipitation regime northward into what is now Central Europe, while leaving the Mediterranean basin itself hotter and drier. The Pliocene proxy record for the Mediterranean region shows this transition. Southern Europe and North Africa were warmer, but also experienced different precipitation seasonality, with the balance between summer drying and winter wetting shifting in ways that have complex consequences for agriculture and water supply. The Arctic Ocean, currently covered by sea ice that reaches its annual minimum extent in September, and is tracked obsessively by climate scientists as an indicator of polar warming, was open water in summer during the Pliocene. This is not a projection. It is documented in the sediments of the Arctic Ocean floor, which contain the remains of organisms that require ice-free conditions for part of the year, and in the El-Gigitgin lake core, whose biological indicators document warm, ice-free Arctic summers. The opening of the Arctic Ocean in summer has consequences that extend far beyond the Arctic itself. The loss of summer sea ice removes one of the most powerful reflective surfaces in the climate system. White ice and snow reflect approximately 80% of incoming solar radiation back to space, while the dark open ocean absorbs approximately 90%. The replacement of sea ice by open ocean in the Arctic summer is a self-reinforcing feedback that accelerates the warming already driven by CO2, and it is already underway. The Arctic is currently warming approximately 4 times faster than the global average, and the Arctic summer sea ice extent has declined by approximately 40% since satellite measurements began in 1979. To live in the period of transition toward Pliocene conditions is to occupy one of the most consequential positions in the history of the species. Every generation of human beings has faced the climate of its time without understanding how it came to be or where it was going. We are the first generation to understand both, to know the mechanism of the warming we are experiencing, to know its trajectory from the physics, and to know its destination from the geological record of the Pliocene. This is a form of knowledge that no previous generation possessed, and that imposes on its possessors a particular kind of responsibility. The responsibility not merely of witness, but of informed agent. The infrastructure decisions being made today have physical lifetimes of 50 to 100 years. Coastal developments built at current sea level in Miami or Jakarta or Shanghai have design lives that extend into a period when, if the committed warming proceeds, and the ice dynamics respond on the faster end of the plausible range, sea level rise of 1 to 2 meters may already be realized. The agricultural investments being made in the Indo-Gangetic Plain, in irrigation infrastructure, in seed varieties, in soil management, are being made in a system whose rainfall and temperature regime is moving toward the Pliocene over the next several generations. The urban planning decisions being made in Saharan and Sub-Saharan Africa are being made for a region whose climate boundary conditions are shifting toward the greener, wetter Pliocene state on the timescale of generations. A shift that represents opportunity for some communities and disruption for others. None of this requires catastrophism. The Pliocene was a habitable world. Its temperature was within the range that complex mammalian life handles with relative ease. Its sea level, while dramatically higher than today, did not cover all the land. Vast areas of the continental interiors remained high and dry. The major mountain ranges persisted. The deep soil systems of the continental interiors continued to support productive ecosystems. What the Pliocene required was a different geography of human civilization. Coastal cities located at higher elevations, agricultural zones distributed further poleward, water management systems adapted to altered monsoon patterns, coastal defenses or strategic retreats where the choice between defense and relocation becomes economically rational. The challenge is not primarily scientific. The science is, at this point, among the most thoroughly verified in the history of natural inquiry. The challenge is the translation of geological knowledge into human decision-making at the scale and speed that the committed warming trajectory requires. Geologists work on timescales of millions of years. Politicians work on timescales of election cycles. The mismatch between the geological reality of the Pliocene commitment and the institutional reality of human planning horizons is, ultimately, the central problem that the Pliocene analogy poses. We have read the mirror. We know our face. The question is what we intend to do about the reflection. The geological record is patient. It does not argue. It simply preserves the evidence of what the Earth system does under given conditions, and waits for the species intelligent enough to read it to do so. We are the first species in the history of this planet that has been able to read that record in sufficient detail to understand its own situation, to look at the sediments and say, we have been here before, and here is what it looked like. The question the Pliocene poses is not a scientific one. The science is settled. The question is what we do with the knowledge that the mirror is already showing us our face.